In section 7 of chapter 10, I'm no longer going to be holding your hand like I did in section 6. Section 6, I pulled out the critical pieces that you needed to solve the equation. All I'm going to do now is connect those individual statements with words to make a full-on paragraph. Once again, these are the formulas that we are going to be using. They are from chapter 9, dealing with compound growth and continuous growth. Here's the problem that I'm going to be working on. I try to pick a problem that maybe you could see some context on how you might use this going forward. A virus works by continuously destroying your white blood cells. We know that after 3 hours, a patient that initially had an average of 5,300 white blood cells per sample is now showing only an average of 3,700 white blood cells per sample. What is the rate at which the virus is destroying the white blood cells? And then as a second question, how long until the patient is at a dangerously low threshold of having an average of 500 white blood cells per sample? Now, before I do the problem, think about the context of this. This is something that we use in science. This is something that nurses and doctors and practitioners use. There's something that is infecting a patient. It is causing damage. First thing you need to realize is, what is the rate of the infection? Second thing you need to figure out is, how much time do we roughly have to treat this before something dangerous possibly occurs? So in this example, I am going to be using the continuous growth and decay function. How do I know that? Well, 2 ways. 3 ways, actually. 1, it's dealing with biology. Biology's nature. Nature traditionally follows this model. Second, it says the word continuously in the problem. Kind of a giveaway that you're going to use the continuous function. But third, and this is the critical piece, for the compound functions, they will say compounds monthly, compounds daily. It'll tell you how often it's going to grow. It never says how frequently it's going to compound over an interval of time, so I know it can't be the original function we talked about with the 1 plus inside the parentheses. All right, so there's a 2-parter. First part, patient goes in and they initially draw 5,300 white blood cells in their bloodline. So it's 5,300 times E, because E is just a number, raised to the KT. We do not know how fast this virus is destroying. We do not know the rate. That's what we're trying to solve for. So K is just going to stay K. Times T. T is going to represent how long we're going to leave it. And we waited 3 hours between samples, so T is going to be 3. After those 3 hours, when we took another sample, we found that there were 3,700 white blood cells. So that's my final amount. So with this function, we can now determine whatever this virus is, we can determine the rate it is destroying this person's immune system. First step, I'm going to divide both sides by 5,300. That'll give me 37 over 53 equals e to the power of 3k. I want to solve for that k. In order to solve for the k, I recognize it's an exponent. In order to solve for an exponent, I need to use logarithms. Right now it's an exponential form, so I got to convert it to logarithmic form. This is the natural log, because the base would be e, of 37 over 53 is equal to 3k. Divide both sides by 3, and we will get k is going to equal the natural log of 37 over 53, all divided by 3. Whatever that is as a percentage, that is going to be the hourly rate of decay. I don't have a calculator, so I'm just going to leave it as is. Now, part 2 has an interesting extension to this. Part 2 was stating, all right, well, now that we know the rate of decay, can we figure out how long it's going to take, T, how much time it's going to take, until the level reaches a dangerously low threshold of 500 white blood cells per sample. So it's still the same setup. We still start with 5,300. It's still going to be E. But now the exponent, the k value, we now know what that is. The k value is what we found in part 1. So this is going to be part of the exponent. The natural log of 37 over 53, all divided by 3, times my t value, which in this case we do not know how long it's going to take, but that's all going to be equal to, now we have 500 white blood cells that we're looking at. Solve it the same way. Divide both sides by 5,300. That will give me 5 over 53 is equal to e to the power of the natural log of 37 over 53 divided by 3 times t. I know, at least for me, I initially thought that we could utilize property 6 of logarithms because I have e to a power of a natural log. However, that natural log as the power is multiplied by t. That t is going to stick around. I can't bring that inside of the logarithm very easily. At least I don't want to. So I'm just going to convert this from exponential form to logarithmic form. This is going to turn into the natural log of 5 over 53 is equal to the natural log of 37 over 53, all divided by 3 times t. Multiply both sides by the reciprocal, which is 3 over the natural log of 37 over 53. And that'll give us, because when I distribute it to both sides, this will cancel out. T will be equal to the natural log of 5 over 53 divided by, 3 times, divided by the natural log of 37 over 53. And this would be how long I have to wait in hours before this patient reaches a very dangerous threshold of 500 white blood cells per sample.